So yesterday we saw that it's h and k that control shifting of functions. We saw that h shifts the graph left and right. We saw that the value of h is the opposite of what it appears to be because the general equation starts with x minus h. When h is positive, the equation would stay x minus h, but it means that the graph goes to the right when h is positive. When h is negative, if you put a negative value in for h in that expression, the minus minus becomes a plus positive. You'll get x plus h, but it means that the graph goes to the left because the value of h is negative. Normally, when we're looking for the value of k, we use the second expression. We get y by itself. And then if k is positive, the graph goes up. When k is negative, the graph goes down. Talked about the fact that sometimes the k is moved over with the y, like that first expression, and that is only because k causes the graph to go up and down, so it is a transformation of the y values, and so that's why sometimes it's written next to the y on the left. Okay, but that's what h and k do. So today we're going to look at what causes a graph to stretch and what causes it to reflect. We're going to see that these graphs will stretch about either the x-axis or the y-axis. We're also going to see that these graphs will reflect over the x-axis as well as over the y-axis. At the end of this chapter, we'll learn about a different type of reflection, about a different line. But most of them will be about or around or across either the x or the y-axis. So we'll develop an understanding of the effects of reflections on the graphs of functions and the related equations, and we'll develop an understanding of the effects of vertical and horizontal stretches on graphs of functions and their related equations. So, a reflection of a graph creates a mirror image in a line called the line of reflection. Reflections, like translations, do not change the shape of the graph. However, unlike translations, they may change the orientation. Remember the orientation, an example of that would be which way the graph opens. Quadratics open either up or down. So that's what the orientation is. When the output of a function y equals f at x is multiplied by -1, the result is y equals negative f at x, and this causes a reflection in the x-axis, So note where that negative sign is. It is in front of the f. It is in the A position, in front of the f. So this is another piece you're going to have to add to your list of things to memorize for this chapter. That is, when A is negative, you get a reflection over the x-axis. So it says the output. Now the output can either be in front of the y, because it's what you get when you sub values in for x. It's the answer you get. So it's normally the y values, the output. So if we make the y negative, it'll be negative y equals f at x. But then when you divide both sides by -1, you'll get the negative in front of the f, which is what is up here. So whether the y is negative or the f at x is negative, it's the same expression, the same equation, because you can move the negative by either multiplying or dividing both sides by -1. Okay? So when a is negative, we now know you get a reflection over or across the x-axis. When the input of a function y equals f at x is multiplied by -1, the input is the x value. So now you're making x negative. And x is inside the brackets after the f. And that's why it says you'll get y equals f at negative x. And in front of the x in our equation, that's our b parameter. So when b is negative, you get a reflection across which axis, Vish? Need to stay with us, okay? When b is negative, you get a reflection across or about the y-axis. Right? So That's how we reflect graphs. We reflect them over the x-axis. That will occur when a is negative. We reflect them over the y-axis. That occurs when b is negative. So, on the next page, compare the graphs of y equals f at x, y equals negative f at x, and y equals f at negative x. So in these cases, you're given an original graph, y equals f at x. For the first one, we are going to graph y equals negative f at x. So we'll do that on the first graph, y equals negative f at x. This is in front of the f. This means that a is negative 1. And when a is negative 1, you reflect it over the x-axis. So what that means is all the points are the same distance away from the x-axis, just on the other side. If points are originally below the x-axis, they will reflect so they're above the x-axis. If they're originally above the x-axis, they will reflect so now they are below the x-axis. The same distance away from the x-axis, just on the other side. So point A is 3 units below the x-axis. That'll reflect 3 units above the x-axis. Note the x value didn't change. Like the x value for both of these points, A and A prime, the x value is negative 4. It's the y value that changed. It went from negative 3 to positive 3. All right, point B is also 3 units below the x-axis. That will reflect across or over or about the x-axis. It'll now be 3 units above. The y-intercept is not labeled with a letter here, but we can transform that point as well. It is 1 unit below the x-axis. It'll reflect 1 unit above. Point C is one of the x-intercepts. It is 0 units away from the x-axis. Remember, when you reflect it, the distance from the x-axis doesn't change. It just moves from either above to below or from below to above. But the distance from the x-axis doesn't change. C is 0 units away from the x-axis. That distance doesn't change. That point doesn't change. We have a second x-intercept at positive 4. That point will also not change. It is 0 units away from the x-axis. And we have a special name for these points that don't change after a transformation has occurred. We call them invariant points. An invariant point is a point that doesn't change after a transformation. But we have point D, which is 4 units above the x-axis. That'll reflect 4 units below. And point E is 4 units below. That will reflect, so it's 4 units above. Again, the distance away from the x-axis doesn't change. It just changes from above to below or from below to above. So we can now connect all these points with a line, and we'll have our graph. So there's the graph of y equals negative f at x. Again, our a value is negative 1, and that causes a reflection over or across or about the x-axis. And in part B, it says, how are the graphs related? So for this first one, we would say there is a reflection about or around or across the x-axis. And our mapping notation, if you compare the points, like we talked about point A being the point negative 4, negative 3, point A prime was the point negative 4, comma, positive 3. If you compare them, the x values are exactly the same. the y values are opposites of each other. We went from a y value of -3 to a y value of +3. We could have done that by multiplying the y value by -1. The mapping notation is that x comma y maps into x comma -y. The y values are multiplied by -1, and that'll be true for all the other points that we transform. The distance away from the x-axis is the same, so the numerical value of y doesn't change, just whether it's positive or negative, because they're reflecting across the x-axis. All right, so there's that one. And for the second graph, let's do y equals f at -x. The negative sign is directly in front of the x, which is where the b parameter is. In this case, b is -1. And when b is -1, we get a reflection across the y-axis. So the distance from the y-axis doesn't change. What does change is whether you go from the left to the right or the right to the left. Point A is 4 units to the left of the y-axis. That'll reflect 4 units to the right of the y-axis. Point B is 2 units to the left. That'll reflect 2 units to the right. The y-intercept is 0 units away from the y-axis. That distance will not change. Our new point will also be 0 units away. In this case, the y-intercept is invariant. Okay, point C is 1 unit to the right of the y-axis. That'll reflect 1 unit to the left. D is 3 units to the right. That'll reflect 3 units to the left. And E is 5 units to the right. That'll reflect 5 units to the left. We can now join all these points with a series of lines to get our new graph. So if we're going to describe what's happening here, in this case, there was a reflection about the y-axis. And if you compare points, point A was at the point -4, -3. Point A prime is at the point +4, -3. The y values are identical. What changed is the x values. And to get that, you could simply multiply the x value by -1. And so our mapping notation would be that x comma y maps into -x comma y. And below, again, it defines that invariant point, a point on a graph that remains unchanged after a transformation is applied. Any point on a curve that lies on the line of reflection is an invariant point. In the case of the first graph, we reflected it over the x-axis. Any points that are on the x-axis are invariant. The x-intercepts were invariant. In the second graph, it was reflected over the y-axis, so the y-intercept was invariant. Any points on the line of reflection will be where the invariant points occur. Okay? So given y equals f at x, once again, we want to sketch the graphs of y equals -f at x and f at -x. So same as what we did on the previous page. So this first graph, let's do -f at x. Again, the negative is in front of the f. That means a is negative. And when a is negative, you get a reflection over the x-axis. So we're just going to take some points here. I'm going to start with that point right there, the point -3, -4. It is 4 units below the x-axis, so that will reflect 4 units above the x-axis. Same distance away, just on the other side. Next, I'll take that point right there, the point -2, -2. It is 2 units below the x-axis. That will reflect 2 units above the x-axis. Same distance away, just on the other side. Because we're reflecting over the x-axis, the x-intercept is invariant. The next point I'll look at is the y-intercept. It's 2 units above. That will reflect 2 units below. And I'll use this point right there, the point 1, 4. It is 4 units above the x-axis. It will reflect 4 units below. So there's our points. We can draw our line going through them. And the original graph has arrows on the end, so we'll need to put arrows on the end of our reflected graph. To describe what happened here, once again, we would say a reflection across or about or around the x-axis. And when that happened, essentially what we did is we multiplied all the y values by -1. So y maps into -y. The second one, let's do y equals f at -x. So now we have the negative in front of the x. That means b is -1. In the case of the first one, it was a that was -1. And when b is negative, you get a reflection across the y-axis. So this point right there at -3, -4, it's 3 units to the left of the y-axis. That'll reflect 3 units to the right. This point here, 2 units to the left, will reflect 2 units to the right. 1 unit to the left will reflect 1 unit to the right. Because we're reflecting across the y-axis, the y-intercept is invariant. It's 0 units away from the y-axis. This point up here, the point 1, 4, is 1 unit to the right of the y-axis. That will reflect 1 unit to the left. So there's our series of points. We can draw our line going through them. And once again, we need arrows on the end of the line. So in this case, we had a reflection across, around, about the y-axis. Because it reflected across the y-axis, it's the x values that changed. All the x values were multiplied by -1. So there's our mapping notation. Okay. So on this next part, the graph of f at x is shown. Sketch the graph of each. Discuss the invariant points. For question A, we want to graph f at -x. So again, here the negative is in front of the x, which means that's our b parameter. B is -1. And you have to memorize this. When b is negative, you get a reflection across the y-axis. So this point here is 4 units to the left of the y-axis. That'll reflect 4 units to the right. The cusp of this graph is 1 unit to the left. That will reflect 1 unit to the right. And let's take this x-intercept on the right. It is 1 unit to the right. It'll go 1 unit to the left. Really, that's all the points we need here. This is what the graph will look like after a reflection across the y-axis. The invariant point is the y-intercept. It's being reflected across the y-axis. So our invariant point at the y-intercept. It's been reflected across the y-axis, so that's where our invariant point would be. Question B then, y equals negative f of x. The negative sign is in front of the f, which means a is negative 1. And when a is negative, that reflects it across the x-axis. So now the x-intercepts will be invariant. There are two of them. The cusp is 2 units above the x-axis. That'll reflect 2 units below. And those are all the points that we really need to do our graph. So that's what it looks like. Right? So in this case, our invariant points were at the x-intercepts. There were 2 of them. Example 2 says the graph drawn in the thick line is a transformation of the graph drawn in the thin line. Write an equation for each graph drawn in the thick line. So if you look at that first case, a person could make a case just looking at it to say, well, how do we know what axis it's reflected about? It looks like it could be reflected about either axis. However, remember that the invariant points are on the line of reflection. So in the case of question A, the invariant point, the point that didn't change, would be right there. So therefore, because that's the y-intercept, that means the graph reflected over the y-axis, because that's where the invariant point is. So in this case here, we had a reflection over or across the y-axis. And when you get a reflection about the y-axis, that means a is negative 1. And a is in front of the f, so the equation would be y equals negative f at x. Because it was reflected over, I'm sorry, I put that in the wrong area. I apologize. When it reflects over the y-axis, b is negative 1. So I apologize for that. Let me fix it. B is negative 1, and b is directly in front of the x. So it becomes y equals f at negative x. But for the second graph, the invariant point is on the x-axis, which means it was reflected over the x-axis. And when you reflect it about the x-axis, now a is negative 1. And the equation would be y equals negative f at x. Because a is in front of the f. Example 3, write the equation of the image of each of these equations after the given reflection. So the first one, if you reflect it over the x-axis, that means that a is negative. And a is in front of the x. The equation would be y equals negative x cubed. Now, this is a unique equation because it turns out if you let b be negative, you would get the same equation. If you let b be negative, you replace x with negative x. Whatever happens to the x also happens to the bx. Because the x is cubed, the bx would be cubed as well. If you let b be -1 and you cube it, -1 cubed is still -1. So this is a unique equation. Whether you make a negative or b negative, you end up with the same equation in the end. Which means that if we look at the original graph, if you reflected it about either the x or the y axes, you would get the same graph. So let's start with y equals x cubed and see what it looks like. Zoom 6. All right. Now, if you make a negative, it'll be -x cubed. And that's what it looks like. That's the graph after it was reflected over the x-axis, because we let a be negative. But if you look at the original graph, the blue graph, and think about it reflecting over the y-axis, it would look the same. And if we put a third equation in brackets, -x to the power 3. So this equation tells us that now b is negative. And when you hit graph, it's going to happen really fast. It's going to draw it over equation 2 or graph number 2 really quickly in a different color. This one ended up being black. So again, this is a rare case where, because of what the original equation is, whether you make a negative or b negative, the result is the same equation. So therefore, it looks the same. Okay? And that's why the answer to part B is the same. If you reflect it over the y-axis, that would mean that b is negative. Whatever happens to the x happens to the bx. In this case, it's cubed. And when you cube -1, you still get -1. Same equation. And we've looked at these graphs to see that they end up being the same. All right, question C. If you take that equation and then you reflect that graph over the x-axis, when that happens, a is negative. Now, a is multiplied by f at x. The entire function is multiplied by a. So in this case here, you're multiplying the entire function by -1. So not only is it 2 multiplied by -1, the absolute value of x plus 1, is all part of that term. But also the positive 3 is multiplied by the -1, so it becomes -3. And you can check these in your calculator. If we take the original equation, which was 2 times the absolute value of x plus 1 with the plus 3 outside, you can see what that graph looks like. It's a transformation of y equals the absolute value of x. Okay, we know that the x plus 1 means that h is -1, so the graph shifted 1 to the left. We know the plus 3 at the end means that k is positive 3, so it shifted up. We're going to learn about what the 2 does here right away, but it also causes a different transformation. But is a graph of y equals the absolute value of x shifted to the left 1 and up 3, and then there's also another transformation that the 2 causes, which we'll learn about. If you just multiplied the 2 by -1 and not the plus 3 at the end, this is what it would look like. So if we only multiplied the 2 by -1, not the plus 3 on the end. Remember that we have a reflection across the x-axis, so you should have an idea of kind of what that would look like when you graph it. It didn't reflect across the x-axis. It reflected about where the cusp was. So that's not the right equation. It's not reflected across the x-axis. In order to make it work, you have to have the 3 as well multiplied by -1, and now it'll be reflected across the x-axis. So you can always use a graphing calculator to check your equations. Make sure the graph that you get is what it should be. And this is the reason why, again, a is multiplied by f at x. The entire function is multiplied by a. To get a reflection across the x-axis, a has to be negative. So you multiply the entire function, in this case, both terms, by -1. Okay? And then for the last one, you're going to take that equation, you're going to reflect it across the y-axis now. And to reflect it across the y-axis, that means b is -1. B is in front of the x. So in this case, you're just going to replace the x with -x. That's the only change here. The x is replaced with -x to get a reflection across the y-axis. And once again, we can use our graphing calculator to make sure that that is the correct equation. So to do this, we'll have to use brackets here, a couple different sets, one to keep the rational expression together, and another one to keep the denominator of the rational expression together. So I put the denominator of x minus 1 in brackets, and I put that rational expression all in another set of brackets. And then we have a +3 at the end, right? So we can graph it and see what it looks like, and then visualize what it would look like when it's reflected across the y-axis, which is what we should get for our new equation. So again, brackets to keep the rational expression together, as well brackets to keep the denominator together, -x minus 1, close both brackets. The +3 doesn't change. So when I graph this, it should look like the original graph after it was reflected across the y-axis. So the y-intercept should be invariant, which it is, and it definitely looks like it was reflected across the y-axis. So whenever you're writing these new equations, you can always check them on your calculator. Make sure the equation that you get does what it should do. In this case, reflected across the y-axis. Okay? The next question says, consider the graph of f at x equals x squared. Which of the following transformations would result in an identical graph? So you know what the graph of y equals x squared looks like. Spent a lot of time in 20-1 looking at quadratics. Right, that's that U-shaped graph that opens upwards. So when you look at this, I think it makes sense. The only transformation that would result in an identical graph would be a reflection across the y-axis, because the y-axis is the axis of symmetry. The first equation, -f at x, well, if we wrote our equation, that's an a value of -1. It would look like that. That should reflect the graph over the x-axis, which would result in a different graph. So if you go -x squared and graph that, changes the orientation, not identical. So that one doesn't work. For f at -x, now you're going to replace x with -x. Whatever happens to the x also happens to the bx, and that's what we have here. We have a b value of -1. Whatever happens to the x, which in this case it was squared, will also happen to the bx. And when you square -1, it becomes +1. This equation becomes +x squared. So it's the same equation. It'll give you the same graph. Again, when b is negative, you get a reflection over the y-axis, which we said would be the transformation that would give us the same graph. And we can put in our calculator like that, in brackets, negative x, and then square all of that. It gives us exactly the same graph. It happened fast there, but it drew the one color directly over the first one. The next expression is both a reflection across the x and the y axes. Both a and b are negative. So a is in front of the x squared for the b parameter. Whatever happens to the x happens to the bx. Because the x was squared, the bx would be squared as well. So the negative inside the bracket, because it's all squared, will become a positive x squared, but the negative in front of the bracket stays there. So this is the same equation as this first example. It will reflect the graph across the x-axis, which will give us a different graph. And again, we can put that into our calculator. All we would have to do is insert a negative in front of the bracket. And it gives us a second graph that's different, reflected across the x-axis, which is what our final equation that we wrote here also shows us. And let's first cross that one off, because that gives us a different graph. And the third one will be different as well, because if you replace the x with the x plus 1, that's what the equation would look like. Replace the x, which is what's in the brackets after the f, replace that with x plus 1. This shows us an h value of negative 1. That's what it shows us. Whatever happens to the x happens to the x minus h. The x was squared, so the x minus h should be squared as well. So this equation tells us that the h value was negative 1, which means the graph would shift 1 left. Obviously, it's going to give us a different graph. And we can see what it looks like in our calculator by putting in brackets x plus 1 all squared. Second graph goes 1 to the left from the first. So it is a different graph. The only one that gives us an identical graph is that second one. And it's only because the original graph was a quadratic where the y-axis was the axis of symmetry. So when we reflected it across the y-axis, it gave us the same graph. So now let's look at stretching. Example 1 says sketch the graph of the root of 4 minus x squared below. So we can look and see in our calculator what that looks like. So we've got the root of 4 minus x squared. Basically is a semicircle. It has x-intercepts at plus and minus 2. You see, when you let x equal negative 2 and you square it, you're going to get 4. So under the radical, you're going to have 4 minus 4, which is 0. The root of 0 is still 0. As well, when x is positive 2, the same thing will happen. So we have x-intercepts at plus and minus 2. Also, you can see by looking at the graph that the y-intercept is positive 2. If you go into the trace mode, it defaults to the y-intercept where x is 0, and you see that y equals positive 2. So there's the graph of the root of 4 minus x squared. Then it tells us to replace y with 1/3 y. So instead of y equals, it's 1/3 y equals the root of 4 minus x squared. And then to get y by itself, we would multiply both sides by 3 to get y by itself. We're going to multiply both sides by 3. And so in this case here, we have an a value of positive 3. A is in front of the function, in front of the radical. So by replacing y with 1/3 y, the end result is actually that a is positive 3. So let's put this new equation in our calculator and see what it looks like. Keep the original one in there. And I'll put this new one into equation slot 2. So now when we hit graph, and in this normal graphing mode, it appears that maybe that graph, the new one, doesn't hit the x-axis, but it actually does. If I change my graphing mode by going zoom, and normally go zoom 6 for standard, that changes the windows from -10 to +10. Instead, I'm going to choose graph or choice 4 here, zoom decimal. Actually gives us a graph that shows that that graph does actually hit the x-axis, and in fact the x-intercepts are invariant. What this doesn't show is where the new y-intercept is. So if I go into zoom and go zoom standard again, we can now see that the new y-intercept, if I go into the trace mode, and when you do this, it always goes to y1 graph. I want to be on y2 graph, so I'll hit either my up or down arrow key, and it switches it to the next equation. And you can see that the new y-intercept is at +6. The x-intercepts are invariant, but the y-intercept is now at +6. So there's what our new graph looks like. And so what really happened here? Well, what really happened here is that there was a stretch. The graph was stretched vertically, and it was stretched by a scale factor of 3. All the y values on the original graph were multiplied by 3 to get the new y values. And lo and behold, that is our a value. A is +3. The result was a vertical stretch by a factor of 3, which means, because it's a vertical stretch, vertical goes up and down, and on a graph it's the y values that go up and down. All the y values were multiplied by 3. Take the y-intercept of the original graph as an example. That was the point 0, 2. That had a y value of +2. Compare that to the y-intercept of our new graph, which is at +6. If you take a y value of 2 and multiply by 3, you get +6. Also look at the x-intercepts. They were at +2, 0. In each case, the y value was 0, and you multiply that by any number, it doesn't change. Those points were also vertically stretched by a factor of 3. But because the y values were 0, 0 times anything is still 0. So again, the end result here is that we got a vertical stretch about the x-axis, and this is important, it needs to be there, by a factor of 3. Because it was vertically stretched, that means the distance from each point away from the x-axis, that distance was multiplied by 3. So that's why we say it was vertically stretched about the x-axis. And the mapping notation now would look like that. We multiplied all the y values by 3. So x comma y maps into x comma 3y. Part B says, what if you replace y with 2y? So now it'll be 2y equals the root of 4 minus x squared. And now if you divide both sides by 2, which is the same as multiplying by a half, there's the equation that you get. This is now an a value of a half. So what should happen is we should now get a vertical stretch by a factor of a half. All the y values should be half of the y values of the original graph. So if I go to my calculator now and insert a third equation, where a is a half, or 0.5, and it's kind of hard to see, it's so small, but if I change to zoom decimal, get a better look at it. The y-intercept is half of what it was from the original graph. The original graph had a y-intercept of 2. Now the y-intercept is 1, half of it. The x-intercepts are invariant. At the x-intercepts, the y values are 0. Multiplying 0 by any scale factor doesn't change it. So I have the same x-intercept. The y-intercept is now at positive 1 instead of positive 2. And the graph looks something like that. So what happened here is, in this case, we had a vertical stretch about the x-axis by a factor of 1/2. And our mapping notation, all the y values are multiplied by a half. And once again, the points negative 2, 0 and positive 2, 0 are the only points on the graph of all three functions. Recall that these are said to be invariant because they are unaltered by the transformations. So I've said you've got to memorize all this stuff. H shifts the graph left and right. H is hooked directly onto the x with a plus or a minus. Whatever happens to the x happens to the x minus h. It's in brackets. And the value of h is the opposite of what it appears to be. K shifts the graph up and down. Normally we get y by itself, so it's on the right side of the equal sign. When k is positive, it goes up. When k is negative, it goes down. Now we see that a, when it's negative, you get a reflection across the x-axis, and when the numerical value of a changes, you get a vertical stretch. And that stretch is across or about or around the x-axis. It's a vertical stretch. So a can do two different things. We never say that the stretch factor is negative. When a is negative, that does something different. It reflects it over the x-axis. So when a is negative, you have two different transformations as long as the numerical value changes. The negative reflects it over the x-axis. The actual numerical value of a, the absolute value of a, tells you the vertical stretch factor. You need to memorize this stuff. Okay, so might not be a bad idea just to have a cheat sheet started somewhere in your package where you have A, B, H, K, and you write down everything that they do and refer to it back often, because you got to know this stuff. You're going to be tested on it in chapter 1, chapter 2, chapter 3. It's going to come up in chapters 4, 5, and 6 as well in trigonometry. We're going to do transformations of trigonometric functions. Chapters 7 and 8 deal with exponential functions and logarithmic functions. We're going to be doing transformations of those as well. So this is going to come up in the first 8 chapters, and you're going to be tested on it heavily on the diploma exam. You have to know this stuff. Okay? So however you choose to, whatever method you're going to use to try and remember this stuff, that's up to you, but you need to figure out a way to know this because you have to. So we're going to start with the same equation, but now we're going to replace x. Above we replaced y with something. Now we're going to replace x with something. So for the first one, we're going to replace x with 2x. So our equation would be y equals the root of 4 minus 2x all squared. Remember, whatever happens to the x also happens to the bx. Because the x is squared, the bx would be squared as well. Now we could simplify this a little bit and say this is the root of 4 minus 4x squared. Same equation. But you have to go back to what we did originally. We replaced x with 2x, so now the b value was positive 2. Right? We replaced x with 2x. B is what's directly in front of the x. So in this case, the b value is positive 2. Back to the graphing calculator we go. And now y2 will be the root of 4 minus, and you can either use our original expression with the 2x all in brackets squared, or a simplified one. Whoops. I got plus there. I need to make a minus. There we go. And that's what it looks like. And if you did 4 minus 4x squared without the brackets, it would be the same thing. So now when we hit graph, the y-intercept was invariant, but the x-intercepts changed. The x-intercepts are half of what they were originally. We went from x-intercepts of plus and minus 2 to x-intercepts of plus and minus 1. The x-intercepts are half of what they were before. And in fact, all the x values are half of what they were before. What really happened here is we had a horizontal stretch, but the stretch factor is half because the x-intercepts are half of what they were before. So we would say in this case is that we have a horizontal stretch about the y-axis by a factor of 1/2. That's what happened. The graph shows us that. The y-intercept stayed the same. So it wasn't a vertical transformation. The x-intercepts are half of what they were before. And even though you can't really see on the graph, all the x values are half of what they were before. And we could prove that if I go back to the calculator. I'm going to draw a line y equals 1. It intersects both graphs. And I'm using this to show that all the x values are half of what they were before. So for example, if I wanted to find the point of intersection between the first graph and the line y equals 1, I'm going to find the point of intersection on the right because there's 2 places where that line y equals 1 hits that first graph. I'm going to find the one on the right. I'm going to go second function trace. I'm going to go number 5 for intersect. My first curve will be my first equation, right? Y equals 4 minus the root of 4 minus x squared. So I can hit enter. That's my first equation. But my second equation, my second curve has to be the line y equals 1. There we go. So I hit enter and enter, and the point of intersection is where x equals 1.7320, and it's a long decimal. Okay? So the point of intersection between the line y equals 1 and that second graph should be half of this x value. Half of 1.7320,508. So if I quit out of here and I go x divided by 2, it'll take my last x value I had for my graph, that 1.73 decimal, and divide it by 2. That's what it works out to be, 0.866025. So let's go back to the graph now and find the point of intersection and make sure it's that decimal. Second function trace, number 5 for intersect. Now my first curve has to be the second equation. Okay, let me try this again. Second function trace, number 5 for intersect. I have to be on the second equation, which I am. There we go. And my second curve will be the line y equals 1. There it is. And there we go. We get the right decimal. 0.866024. 0.860254. So that just proves that all the points are found by taking half of the x values from the original. We had a horizontal stretch by a factor of 1/2. All the x values are half of what they were before, so x comma y would map into 1/2 x comma y. Now, the next part of this tells us to replace x with 1/3 x. So it'll be the root of 4 minus 1/3 x, all squared. Remember, whatever happens to the x happens to the bx. The x was squared, so the bx will be squared as well. And you could simplify that. You could square the 1/3 x, and you'd get 4 minus 1/9 x squared. Okay, so let's put that in our calculator now. This is the root of, and I'll use brackets here to go 1 divided by 9. Close the bracket, and then I have my x squared. So that looks right. I'll clear that third equation out of there, and I graph it. Again, the y-intercept was invariant. The x-intercepts changed. They went from plus and minus 2, 0 to plus and minus 6, 0. All the x values were, in this case, multiplied by 3. Right? Our first x-intercept on the right was at 2, 0. It's now at 6, 0. The x value is multiplied by 3. Same thing with the x-intercepts on the left. -2 became -6. The -2 was multiplied by 3. So in this case here, we would say that there is a horizontal stretch about the y-axis by a factor of 3. all the x values were multiplied by 3, so our mapping notation would be x comma y maps into 3x comma y. So let's look back and see what actually happened here. In the case of that first scenario that we did, and we didn't draw the graphs on our grid for this one, but we definitely could, where the first one, the original graph was just 4 minus x squared. And then we did 4 minus 2x squared in blue, and we saw that that caused a horizontal stretch by a factor of a half. So now the x-intercepts were plus and minus 1 comma 0. And then we did, when b was 1/3, they went to plus and minus 6 comma 0. But when you compare the original graph to the blue graph, it horizontally stretched by a factor of a half, but the b value was 2. A b value of 2 causes a horizontal stretch by a half, and a half is the reciprocal of 2. In the case of the last graph, our b value was 1/3, and we saw that we got a horizontal stretch across the y-axis by a factor of 3. The scale factor 3 is the reciprocal of the b value of 1/3. So that's what happens when b, the numerical value of b, changes. You're going to get a horizontal stretch about the y-axis, but the stretch factor is the reciprocal of b. When the numerical value of a changed above, we saw that it caused a vertical stretch, but the stretch factor was the absolute or actual value of a. So on the next page, it kind of summarizes all of this. A stretch, unlike a translation or a reflection, changes the shape of the graph. However, it does not change the orientation. When the output of y equals f at x is multiplied by a non-zero constant a, you're going to get y equals a times f at x, or y over a equals f at x. This causes a vertical stretch about the x-axis by a factor of a. And it says the absolute value of a there because when a is negative, again, that does something different. It reflects the graph over the x-axis. When the input of f at x is multiplied by a non-zero constant b, the result is y equals f at bx. And this causes a horizontal stretch. It's stretched about the y-axis, but the stretch factor is 1 over the absolute value of b, the reciprocal of b. And when b is negative, that does something different. It reflects it across the y-axis. So again, you need to memorize this. You're going to be tested on it multiple times, so you need to know it. Okay? So there's an assignment there for you to work on. Again, I will post the solutions to Google Classroom so you can check your answers. There's questions on both pages. And actually, I think in this case, I'm actually going to collect this for marks. So you're going to rip it out of your package. You're going to put your name on it. And you're going to hand it in on the filing cabinet there. I'll move that stuff off there so you can put it there. So make sure you put your name on it. You're going to hand it in. I'm going to collect it for marks. It'll go into Power School as your first assessment for this course. Okay?